I would like to demonstrate for you the ISO CBCT Plus module designed to determine the position and size of all radiation isocenters of your LINAC, as well as to determine the radiative gantry, collimator, and couch rotation angles. The position and size of all radiative isocenters, the MV isocenter, that means the treated isocenter, the isocenter of the IGRT system used in planar mode, and the IGRT isocenter in CBCT mode using the Winston and Lutz test. But with this test, you acquire images at different gantry, collimator, and couch rotation angles to find all rotation axes of the machine, which provides a good opportunity to also test these rotation angles. As you recall, my images are on the welcome screen. I will use a Varian example first and then a Siemens example. These images come from a clinic used in Sweden. We would of course normally use the analysis button, and the reports would be rapidly displayed, but for our purposes I would use the step-by-step mode to take an in-depth look at the analysis. I will now use the All Tests button in the step-by-step mode, which enables all tests to be initiated with one click. While this is being done, I will present the test object which is recommended using to carry out the Winston and Lutz test. I will show you a short video clip which explains how the test object functions and how to install it under the LINAC. The QUALIMAGIQ test object is pictured. The program can also handle other test objects, for instance the Winston and Lutz test object manufactured by PTW, or the models supplied by Elekta or BrainLab, but you will see that our test object provides many advantages. It is made of an acrylic sphere 10 cm in diameter with a 5 mm diameter tungsten ball in its center. The sphere is etched with 3 equatorial white engravings which are used to align the central ball of the isosphere on the 3 lasers lines. These white engravings set on a black background enable you to align the sphere on the lasers without using a sheet of paper. Most often, you have nice white test objects with black engravings, and in order to align them on the lasers, you need a sheet of white paper to see the projections of the laser on the black engravings. We are particularly attentive to this point. When an object needs to be aligned on lasers, the engravings are white. When an object needs to be aligned on light, the engravings are black. For this reason, here they are white. The sphere is supported by a stainless steel plate which acts as a counterweight. A carbon rod connects the sphere to the plate. It has a metal ring which can be detected on the images, which will be used for measurements. Given that when the test object is placed on the couch and it rotates, the ring will move as well. The plate also bears white engravings which will be used to pre-align the test object and to verify before starting the Winston and Lutz test that the lasers are orthogonal, level and coincident with the surface of the sphere. A certain precision is required in terms of level, so the test object is fitted with 3 adjustable leveling screws for this purpose. This is summarized here. Our test object enables you to verify that the lasers are set correctly before to determine the radiative isocenters of your treatment machine, as well as the radiative rotation angles. These radiative rotation angles are important because you could very well mechanically adjust your gantry at 90 degrees and check it with a precision spirit level, yet due to Earth's magnetic field and due to bending of the coils in the head of the machine. When you are at 90 degrees mechanically, you are not at 90 degrees for the treatment. As we use for the Winston and Lutz test images acquired with the MV imager, in other words radiation beams, we will determine the treatment rotation angles in the images. How do we use the test object? We will begin by removing it from the protective aluminium case in which it is supplied and placing it at the end of the couch. First, you will adjust the couch for rotation at 0 degrees. Lateral couch at 0 with a couch height of around 7 centimeters. The following step is to align the plate, proceeding in the following order. Align the sagittal line of the plate along the sagittal laser. This is done by hand in order to gain time. Next, you will adjust the level. As you see, when you adjust the level, nothing changes with the sagittal line because the spirit level is on the sagittal line. Using the couch lens movement, we will align along the transversal line of the plate. You can already check whether your lasers are level and orthogonal. You will then use the couch vertical movement to line up with the lateral engravings. The plate is now perfectly aligned. The next step will be to align the sphere. You will move the couch 25 centimeters towards the fit to line up with the sphere. Given that the couch is empty, there is a slight tilt. You will see that the technician will use the couch height movement to compensate for the tilt and return onto the white engraving. Here you will notice just how efficient the white engravings are in order to distinctly see the lasers, eliminating the need for a sheet of paper. We will remain on this view as there are several interesting things to look at here. The tungsten ball inside the sphere is aligned on the equatorial engravings. You can now say that the lasers are aligned on the tungsten ball, and the tungsten ball, which will be visible in the images, represents the intersection of the laser planes in the treatment room. All this for the Winston Lutz test. Here, on the periphery, you see a pair of tungsten balls. In fact, there are 3 pairs of balls, one at the top, one at 120 degrees on this side, and one at 120 degrees on the other side. When the gantry rotates, the distance between the central ball and the pairs of peripheral balls will evolve according to the gantry rotation angle. By determining the distance between the central ball and the pair of balls, the gantry rotation angle can be determined. That is, the radiation or treatment angle. For the metal ring, given that the object is placed on the couch, when the object will rotate, the ring will rotate, and as the ring is detected in the image, we can determine the couch rotation angle. Insofar as the collimator is concerned, I will return to the video. You see 2 small plates which we have not yet discussed. These are the cross-test objects, the KV and the MV test objects. The KV test object is placed at the X-ray tube exit. The MV test object is placed at the collimator exit. The KV cross-test object is not used with variant true beams, as the tube is beneath the cover. True beam use isocal compensation, which always places the imager opposite the source. These two cross-test objects are used to compensate for the stray movements of the imager relative to the treatment source, which are due to the imager sagging when the gantry rotates. The center of the cross-test objects, formed by its four tungsten balls, creates a fixed reference point originating from the source. We set this up at the MV collimator exit and at the X-ray exit when possible. And in these MV images, we detect the ring of the isosphere holder to determine couch rotation angles, the peripheral balls of the ISO to determine the gantry rotation angles, and the rotation of the cross-test objects to determine the collimator rotation angle. Once we've done a good job here, we see that the sphere is perfectly aligned, and I repeat, the central ball corresponds to the intersection of the laser planes. We are now able to begin the Winston and Lutz test, which will consist in acquiring MV images of the ISO and cross phantoms at various gantry rotation angles. This will determine the machine's gantry rotation axis in MV. We do the same for various collimator rotation angles to determine the collimator rotation axis in MV, and then again the same operation for the couch to give us all three MV rotation axes for the machine. We will then repeat the procedure in KV, but of course without collimator rotation to determine KV isocenter, and then we will scan the sphere of the isophantom in CBCT to determine the CBCT isocenter. We will now return to QUALIMAGIQ, which has completed its job, which consisted in detecting in all of the images the four balls of the cross-test object, the central and the six peripheral balls of the isophantom and its metal ring. When the gantry rotates, we can see that the peripheral balls move relative to the central ball, with which we can determine the gantry rotation angle. When the collimator rotates, the cross-test object will rotate, and we will determine the collimator rotation angle. Then, when the couch rotates, we detect the ring and determine the couch rotation angle. By studying the movements of the central ball relative to a reference point originating from the source, the cross-test object center, we carry out the Winston and Lutz test. If the central ball and thus the lasers are really on the gantry rotation axis, when the gantry rotates, the central ball should never move in images. If the central ball moves, that means that the lasers are not on the gantry rotation axis. So by studying the movement of the central ball relative to a fixed point originating from the source, we can determine the machine's gantry rotation angle. We proceed in the same manner for the collimator and for the couch, and we determine the treatment machine's three rotation axes. We will repeat the above in KV, gantry rotation axis. We rotate. You see that here the same is done when the couch is moved, here the couch is turning. This is not mandatory, nor it is very practical, because when you acquire the KV images, the tube is at 0 degrees, the head of the machine is at 90, and so it is very inconvenient to turn the couch, as it risks colliding with the head. Furthermore, determining the couch rotation axis in KV in planar mode is of no real interest, because as the couch is independent from the gantry, to look at it with the MV source is the same rotation axis as with the KV source. Obviously, this is not the case for gantry rotation axis, because the X-ray tube and the treatment head are on board for the gantry rotation. Here, the couch rotation axis has been measured in KV, even though it is not very practical and, I repeat, not necessary. In the last step, we will scan the sphere in CBCT. You see that we detect the surface of the sphere. In the first solution, we detect the center of the central ball, but due to the artifacts, we prefer to retain this as the first solution. But after this first solution, we detect the sphere surface, and by applying a spherical regression to all of the sphere points and by determining the center of this spherical regression, we determine the coordinates of the sphere center in the CBCT coordinate frame. In other words, these coordinates of the lasers, since the sphere is aligned on the lasers in the CBCT coordinate frame. Once the software has taken all these measurements, it displays a 3D view. I will set the gantry rotation axis facing us. Here, we are just about directly across from the machine, a bit in profile. The MV gantry rotation axis is in red. The KV gantry axis is here in purple. The collimator rotation axis is the blue axis, and the two couch axes are MV in yellow and KV in orange. You can see this reflects precisely the situation described earlier on. The couch axis in MV or KV is the same. Deviation couch position 0.1 mm, which is the degree of accuracy of the program, so you can say that the axes are together. Now it is all a matter of definition. How is the ISOCENTER defined? QUALIMAGIQ contains 8 different ISOCENTER definitions, and we will see that the definition the client selected is to force the MV ISOCENTER, the green point, onto the gantry rotation axis and between the collimator rotation axis and the couch rotation axis. This is quite a classical and logical definition, to force the ISOCENTER onto the gantry rotation axis, which is the main treatment axis, as I want the tumor to be on the gantry rotation axis, and this is even more true with VMAT, in which the gantry rotates through the entire treatment. For the KV ISOCENTER in planar mode, you have here the KV gantry rotation axis, and you see they placed themselves at the vertical projection of the couch on the horizontal axis of the gantry. These are logical definitions, but other definitions are available for use in QUALIMAGIQ. We determine the position of the rotation axis, but also their size. For instance, during gantry rotation, the rotation axis moves when the gantry rotates. This is due to wobble, due to wear and tear of the ball bearings, all of which results in your axis, which should have been very small, becoming a tube. This screen shows the size of the rotation axis. The biggest axis on a new machine is the gantry. The biggest axis on an older machine is the couch, which shows play from bearing the weight of patients. The collimator rotation axis, represented here in blue, is always the smallest axis of a treatment machine. Quantitative data is supplied here as well, which we will examine when we look at the analysis report, which is now displayed. The most important parameters are displayed in blue. As there is a cross-test object at the head, we are able to determine the movement of this cross-test object on the imager, which will in turn determine the sag of the MV imager when the gantry rotates. The same holds for KV, with the cross-test object placed at the X-ray tube exit. Its movement on the imager will describe the KV imager sagging. Given that we detect the surface of the sphere, it is interesting to measure its radius and compare it to its theoretical radius, which is 51 mm, which yields a geometrical distortion test in the CBCT images. As you can see, they use 5 collimator angles, 5 gantry angles, 5 MV couch angles, and we will find the greatest deviation in rotation angle for the collimator gantry and couch around 0.3 to 0.4 degrees. None of these tests are related to Winston and Lutz. We get the most we can out of the images to provide the most information we can. For instance, it would be a shame not to test rotation angles here, where everything is rotating and moreover where it is tested from a radiative rather than a mechanical standpoint. We will now start on the Winston and Lutz test results. We indicate what needs to be done to position the lasers opposite the 6 MV treatment isocenter. What needs to be done for IGRT used in planar mode to reposition the imager opposite the treatment isocenter. And what needs to be done for IGRT in CBCT mode to set the system opposite the treatment isocenter. For the treatment isocenter, MV isocenter, the size of the gantry rotation axis, the size of the collimator rotation axis, and the size of the couch rotation axis. By measuring the head, foot, and longitudinal movement of the cross-test object, we can also determine the gantry flex. In other words, the head-foot movement of the source when the gantry rotates. The same is possible for KV, the size of the gantry axis, the size of the couch axis, and gantry flex in KV. In other words, the head-foot movement of the X-ray tube when the gantry rotates. There is one parameter we have not yet discussed, the size of the treatment isocenter and of the KV isocenter. How is isocenter size determined? We will pull up a graph. We are looking at the treatment machine from above, and we will look at the size of the isocenter in this frontal view. The green point is the MV isocenter. We will zoom in on the gantry axis in MV, which is here, seen from above in red. The couch axis in MV is this yellow cylinder. The collimator axis in MV is this blue cylinder. The yellow and blue cylinders are vertical. The red cylinder is horizontal. If we did not take the flex into consideration, the box encompassing the isocenter would be limited by the collimator tube at the bottom, by the couch tube to the right, and by the couch tube at the top, and by the gantry tube to the left. When the flex is taken into consideration, the size of the isocenter is increased in the head-foot direction. You can see that we are above the collimator tube and the couch tube. You see that we have centered the flex on the isocenter. Why? Because the flex was determined by the movement of the cross-test object in head-foot direction, and you do not treat with the cross-test object, you treat with beams. So we are able to determine the amplitude of the flex, but we are not able to position it in space. We will see later on, with the Siemens example, that by detecting the field edges in addition to the cross-test object, we are able to correctly position the flex in space. We will return to the analysis. We have determined the gantry rotation axis by studying the movements of the central ball relative to the cross-test object. We will return to the graphs and look at this graph, which will enable us to determine the position and size of the gantry rotation axis. We are facing the linac in a transverse plane. The origin of the graph is the central ball, therefore the lasers, and the red lines introduced correspond to the measurements made in the MV images. For instance, how is this red line at 144 degrees positioned in the graph? We measure in the portal images the transverse or right-left distance between the central ball of our ISO phantom and the center of the cross-test object, and we re-enter this transverse distance orthogonally relative to the red line, which is oriented according to the rotation of the gantry. The same is applied to all lines, that means for every gantry angle tested. We then detect the minimal circle capable of encompassing all of these lines. The center of this circle is the intersection of the gantry rotation axis and the transversal plane passing by the central ball of the ISO phantom, so the laser isocenter. To determine the size of the axis, we will use the greatest deviation between all the lines and the minimal circle. Here it is for 288 degrees, and this greatest deviation is equal to the diameter of the rotation axis. It's a bit complicated to determine the gantry rotation axis because the portal imager is not perpendicular to the rotation axis which we are studying, but rather parallel to the horizontal gantry rotation axis. It's a little bit easier for the collimator because its rotation axis is orthogonal to the portal imager. That means its rotation can be directly observed on the portal imager with the rotation of the center of the cross-test object relative to the central ball of the isotest object. In other words, the laser isocenter. This is illustrated in this graph, which shows all of the impacts of the center of the cross-test object on the imager, all of the red points pictured, and we will determine the optimal circle who best includes all of these impacts. In other words, the circle which will minimize the sum of the squared deviations between the circle and the points. The center of the circle is the intersection between the collimator rotation axis and the frontal plane passing by the laser isocenter. For the side of the collimator rotation axis, its radius, not the diameter here, will be equal to the greatest distance separating the points from the optimal circle. The same holds for the couch, only here we have a half rotation. What is in rotation for the couch? Not the cross-test object, which no longer turns, but rather the central ball of the isotest object. We will look at the rotation of the isotest object relative to the cross-test object. This yields all of these points which are best included by the optimal circle. The center will be the couch rotation axis on the frontal plane, and the greatest deviation between the optimal circle and the points will correspond to the radius of the couch rotation axis. This is purely the Winston and Lutz test. One more thing concerning the measurement of the gantry rotation axis. You see that when the gantry rotates, the three pairs of peripheral balls evolve. The distance between them and the central ball changes. This distance describes a sine curve. 3 curves for 3 pairs of balls. We will take a closer look at the red sine curve, which corresponds to the balls at the top of the sphere. When the gantry is at 0, the distance between the central ball and this particular pair of balls is 0. We are at this point on the graph. The y-coordinates on this graph are the gantry angles. When the gantry rotates, the distance increases. You can see the distance in red gradually increasing up to a maximum, which is the radius of the sphere when the gantry is at 90 degrees. From there, the distance decreases, returning to a distance of 0 at 180 is the same as it was at 0 degrees. As we head towards 270 degrees, the distance will increase, but it will be negative. You can note that the distance between the peripheral balls and the central ball, according to the gantry angle, describes a sine curve. So if you know the distance, you know the angle. There is just one slight problem with a certain pair of balls. You notice that at the peak of the sine curve here, when the gantry angle increases or changes, the distance does not vary much. The maximum distance is here, the sphere's radius, so you have a precise measurement of the distance but not a sensitive method to determine the gantry rotation angle because the distance does not change when the gantry slightly turns. You think that in order for it to be sensitive, the curve needs to have a steep slope. The strongest slope of a sine curve is when it is equal to 0. So it is indeed sensitive here. We observe that the distance varies a lot when the gantry rotates. However, the distance is very short, so it is not very precise. So at 4 times the curve of a given pair of balls, for instance the red pair, is precise and sensitive. They correspond to the intermediate angles 45 degrees here, here and here. You would be very disappointed if you could obtain correct gantry angle measurements for only 4 rotations. This is why we added 2 additional pairs of balls at 120 degrees from the pair at 0 in order to create 3 sine curves with 3 different phases to yield 12 times in the rotation at which you can measure gantry angle with precision. To recap, to determine collimator angles, we only examine the rotation of the cross-test object, and for the couch rotation angle, we examine the rotation of the metal ring. To conclude, I will show you how better to take the flex into account when determining the size of the isocenter. I will use a Siemens exam to illustrate this. I will enter the step-by-step mode to see how to correctly position the flex in the space of the treatment room. I start all tests, which you will notice contains an additional step. Field center. We will detect the radiation field in all of the MV images. This is illustrated here. The radiation field is detected with the field center, and we will examine how the field center shifts in the head-foot direction when the gantry rotates, same as with the cross-test object, except that here patients are actually treated with a radiation field and not with a cross-test object. In this case, we will be able to position the flex in the space of the treatment room and correctly take the flex into account in the size of the isocenter. The next step is to detect the peripheral balls in order to measure gantry angle. The following step, isocenters and rotations, uses all of the measurements made in the preceding steps to solve the problem of geometry in space, to determine the radiative isocenters and the rotation angles, which is the objective of this module. It takes a while to detect the peripheral balls, as there are 6 of them, with a lot of images. On the subject of images, how long does this take? For 5 gantry, 5 collimators and 5 couch images in MV, it takes 15 minutes. To which you add 5 gantry in KV, which takes 5 more minutes, so far 20 minutes, and then you scan the sphere in CBCT in 1 more minute. So in less than 25 minutes you have made the acquisitions to test all of your treatment machine's radiative isocenters, the laser isocenter and all of the rotations, gantry, collimator and couch, from a radiative standpoint. Now that it has finished, I'm interested in this graph. So I will zoom in on the green square, and you observe that the difference with earlier on when the flex was centered on the isocenter, the flex is now taken into account insofar so amplitude is concerned, but especially relative to its positioning in space. This enables us to see that in fact the box encasing the isocenter, in other words the size of the isocenter, is strongly influenced by the flex, which has a tendency to pull the isocenter towards the head. The results here are rather different from the previous results. This concludes our demonstration of the ISO CBCT Plus module. Thank you for your attention.